my name is Lorraine Kyles, and this is my Chem Lab final presentation. So the first slide is on the periodic table. The periodic table is made of groups and periods, which help show how elements act in different situations. The vertical columns on the periodic table are called groups. Elements in the same group have the same number of valence electrons, which means they have similar chemical and physical properties. This is why elements in the same group tend to make the same kind of ions and react in the same way. So on the next slide, we have examples. For instance, lithium, sodium, and potassium are all in group 1. The atomic number of lithium is 3, and its atomic mass is about 6.94. Potassium has an atomic number of 19 and an atomic mass about 39.10, while sodium has an atomic number of 11 and an atomic mass of 22.9, because they all have one valence electron. These metals are all very reactive. And then I have some more examples on there. All these elements have 7 valence electrons and usually make an ion with the charge of -1. So the next slide, we have the periodic table part 2. The horizontal rows of the periodic table are called periods. When you move from left to right across a row, the chemical properties of the elements slowly change, but they all have the same number of electron shells. The atomic number goes up by 1 for each element, which changes the size, electronegativity, and the reactivity of the atom. So my next slide, I have examples for this. For instance, period 2 has lithium, carbon, and neon. All these elements have 2 electron shells, but they act differently. Another example is period 3, which has sodium, magnesium, and argon. All these elements have 3 electron shells, but they act very differently chemically across the period. So this next slide is about electron configuration. And I have 2 examples, which is magnesium and chlorine. Electron configuration shows how an element's electrons are arranged. And it helps to explain why elements behave differently. These 2 examples show how electron configurations differ across groups and why elements in different groups react differently. So my next slide is about flame tests. Flame tests and spectroscopy show that each element has its own chemical and physical properties because of how its electrons take in and give off energy. When you do a flame test, metals give off different colors. For example, sodium gives off a bright yellow color and copper gives off a blue-green color. This is because the metal's electrons jump to higher levels and fall back down, which releases light. My next slide is about the spectroscope. A spectroscope separates this light into different wavelengths, which makes a pattern of colored lines called the emission spectrum. For instance, sodium has a strong yellow line of about 589 nanometers, which has a frequency of about 5.09 times 10 to the 14th power hertz. This wavelength is what makes it yellow. Scientists can find elements in samples that they don't know about by using these unique wavelengths. This method is used in chemistry labs, forensic testing, and even astronomy.
Go.
The formula for glucose is C6H12O6. This is a bigger example. It has 6 carbon, 12 hydrogen, and 6 oxygen atoms. Chemists use these formulas to learn about the makeup, structure, and behavior of different things. So my next slide is about stoichiometry. Stoichiometry is the part of chemistry that tells us how much each substance is needed or made in a chemical reaction. Before you can do this right, you need to balance the chemical equation. This means that the number of atoms of each element is the same on both sides. This is in line with the law of conversion of mass, which says that matter can't be created or destroyed. For instance, the unbalanced equation for the reaction between hydrogen and oxygen to make water is H2 plus O2 makes H2O. To make it equal, we put a 2 in front of the H2 and H2O, which makes 2H2 plus O2 equals 2H2O. There are now 4 hydrogen atoms and 2 oxygen atoms on each side. Once you have balanced the equation, you can use the stoichiometry to figure out how much is something you need. For example, we can find out that 2 moles of hydrogen will make 2 moles of water. So the next slide is about molarity. Molarity is a way to talk about how concentrated a solution is. It is the number of moles of solute per liters of solution. A mole has Avogadro's number in particles and its weight in grams. It's the same as the molecular weight of the substance. 1 mole of sodium chloride weighs about 58.44 grams, which is the molecular weight of NaCl. The molarity of a solution is 0.1 moles if you dissolve 1 mole of NaCl in enough water to make 1 liter of it. Chemists can accurately make and figure out concentrations of solutions because the link between moles and molecular weight and volume.
That's 0.1.
So the next slide is about acid-base reactions. Acid-base reactions occur when acid donates a proton and a base that accepts the proton, forming new products. Acids typically produce H plus ions in water, while bases produce OH negative ions. And when they react together, they usually form water and a salt. For example, when a hydrochloric acid reacts with sodium hydroxide, the H plus from the acid joins with the OH negative from the base to create H2O, and the remaining ions form NaCl, a salt. The balance equation is HCl plus NaOH makes H2O plus NaCl. These reactions are important in many processes such as digestion, neutralization of stomach acid, and maintaining a pH balance in chemical systems. In single and double displacement reactions, elements or ions switch places, but they do it in different ways. One element takes the place of another in a compound during single displacement reaction. When zinc and hydrochloric acid react, zinc takes the place of hydrogen, making zinc chloride and hydrogen gas. 2 compounds swap ions with each other in a double displacement reaction to make 2 new compounds. These reactions help figure out what things are, make precipitates, and show how ions work together in solutions. The three-dimensional shape of a molecule is called its molecular geometry. This shape is determined by how the electron pairs are arranged around a central atom. Vesper theory says that electron pairs push each other away and spread out as much as they can, which makes shapes that are easy to guess. For instance, the molecule CH4, methane, has 4 bonding pairs and no lone pairs around the central carbon, which gives it a tetrahedral shape. H2O, water, on the other hand, has 2 bonding pairs and 2 lone pairs on oxygen. This makes the molecule bend into a V or bent shape. It is important to know about molecular geometry because it changes how polar, reactive, and physically stable a molecule is. Molecular geometry is important in many fields because the shape of the molecule affects how it works in chemical and biological systems. The shape of a molecule affects its polarity, which in turn affects things like how soluble it is, its boiling point, and how strongly it interacts with other molecules. Molecular shape is very important in medicine and biology because enzymes, hormones, and drugs must fit together like lock and key to work. In chemistry and materials and science, knowing about geometry can help you guess how reactions will go, make new compounds, and make useful things like plastics, detergents, and batteries. Molecular geometry is used in environmental science to figure out how gases like CO2 and the ozone work together in air. Molecular geometry is important for predicting and designing how chemicals will behave in the real world because the shape affects so many other properties. An empirical formula shows this slide is about the empirical formula. An empirical formula shows the simplest whole number ratio of an element in a compound, unlike a molecular formula which gives the exact number of each type of atom in a molecule. The empirical formula reduces those numbers to their lowest ratio. For example, glucose has the molecular formula C6H12O6, but its empirical formula is CH2O because of all the subscripts can be divided by 6. Another example is hydrogen peroxide, which has the molecular formula H2O2, but its empirical formula is HO. Empirical formulas are useful because they provide basic information about the composition and compound and are often determined through experimental data, especially when analyzing unknown substances. A molecule or accurate formula tells you how many of each types of atoms are in a molecule. The molecular formula tells you the real makeup of a compound, while the empirical formula only gives you the simplest ratio. The molecular formula of glucose is C6H12O6, which means that each molecule has 6 carbon, 12 hydrogen, and 6 oxygen atoms. The molecular formula of hydrogen peroxide is H2O2, which means that it has 2 hydrogen atoms and 2 oxygen atoms. Molecular formulas are important because they show what a substance really looks like and what it is. You can only find out what they are if you know both the empirical formula and the compound molar mass. And this is the gallery for the pictures I couldn't fit in the slide. And these are the references. So, thank you.